14.5 Triple Integrals in Cylindrical and Spherical Coordinates. What I'd like to do in this video is to just look at the ebook with you. So I'm just going to guide you through reading the ebook, which you can certainly do yourself, and I'm happy to have you just turn off the video and explore it yourself. But if you'd like to explore it with me, let's do it. A point in cylindrical coordinates is represented by r, theta, and z. R, let's look at what happens as I move r. R is the distance from the z-axis to the point. So here r is equal to 5. The point is 5 units from the z-axis. And here r is equal to 0. The point is a distance of 0 from the z-axis. Let's put it back at 5. Theta. Theta here is in radians. It's not in the pi over whatever that you're used to, but these are radians. So at pi equals 0, your point would have to be on the x-axis somewhere. And for, let's see if we can find pi over 2. Boom. Pi over 2 would put us on the y-axis, and pi would put us on the negative x-axis, 3 pi over 2, and then 2 pi. And let's put it back into the first quadrant. So what, about pi over 3? Now what happens as we change z? Well, it's the same as in Cartesian coordinates. You can have a negative z value that puts you below the xy plane, and you can have a positive z value that puts you above the plane. This really is a fun thing to play with. Let's just reset everything. And now, actually, I think I'd like a radius of 5, because I think that makes things a little more dramatic for me. Let's look at some constant surfaces. A constant surface of r equals 5. This is every point in three-dimensional space that is 5 units away from the z-axis. Now, perhaps we do want to put this at about pi over 2. Gotta have very careful maneuvering here. There we go. So, a constant surface of theta equals pi over 2. That is the half of the zy plane. So you only get half planes. And that's because r is only allowed to be positive. Now let's look at a constant value of z. First, see if you can imagine it. What would be a constant surface in z in Cartesian? Your constant surface in cylindrical would be the same. So a constant surface of z equals 2.5. Well, that's a plane that's going to be parallel to your xy plane. And here are some basic sets. Your cylinder, your cylindrical shell, your vertical half plane. We've seen the cylinder and the vertical half plane. Your horizontal plane, and here's a new one, the cone. So z equals r, or z equals 2r, or z equals half of r. And a is, think of that as your slope. That's going to be the slope of your cone. And now let's come down here and look at the transformations between cylindrical and rectangular coordinates. So if you are comfortable with polar coordinates, you're going to be very comfortable with cylindrical coordinates. Cylindrical coordinates just adds an extra axis of z, so that you don't have to stay in the xy plane anymore. You can come off of it using the z-axis. I think it's time to start talking about spherical coordinates. And I think if I can do this without screwing up, I'd like to move. There we go. All right. So in spherical coordinates, we have three different, I like to use these notes. We have three different values. Okay, so this coordinate rho and should not be confused with r in cylindrical. Why is that? Rho, r is the distance to the z-axis. Rho is the distance from the origin. And theta, let's see what little note we've got there. Theta is, oh, I'm sorry, that's not theta. That is phi. Phi is the colatitude. You're going to see why it's connected with the word latitude. And again, it's not the same as a polar angle. It's the angle between the positive z-axis and your line. Well, I'll show you that in a minute. I apologize if I'm not pronouncing phi right. I always say phi. Maybe it's phi. All right, and then now theta is something that's familiar to you. That is the same as cylindrical coordinates. Okay. Now let's go to our the fun part, the interactive figure. And again, I'd like to try to move this back. There we go. All right, good. No screw up. Okay, so let's first play around with rho. And if rho is 0, that takes you all the way down to the origin. And then as you move away from the origin, rho has to increase. Notice that rho does have to be 0 or positive. We're not going to be using a negative rho. Then let's talk about phi. Phi, I said, is the angle between the line OP and the z-axis. So if did I call that rho? I'm sorry, phi. I'm not sure. I'm not really even sure what I'm saying here. Phi equals 0 puts us on the z-axis, and when phi is equal to pi over 2, boom, that puts us in the xy plane. And now let's keep moving phi all the way to pi. That puts us on the negative z-axis. So phi just moves between 0 and pi. And so it's at pi, and I bring it back up to 0. And now let's get, I don't know, about a 45-degree angle. All right, now theta. Theta is an old friend. Theta, again, if theta is equal to 0, we're on the x-axis, and theta is equal to pi over 2, and pi, 3 pi over 2, and 2 pi. Okay, now here's some really fun stuff. Let's look at some constant surfaces. I think I'll reset everything, and then as before, move my row to the biggest because I like big. Okay, so let's look at a constant surface of rho. Rho equals 5. What is that? Well, that's every point that's a distance of 5 from the origin. Let's look at a constant phi surface. So phi is 1.5, and every point rho phi theta, where phi stays constant, will give us that surface. And let's move phi so you can see. So depending on how tight you want your cone to be, or maybe you want it to point down, that's what you use your choice of phi for. And now let's look at a constant theta. A constant theta surface, the half plane again, just like in cylindrical. Okay, well that's something that we can count on. All right, now what if I were to put my constant rho surface there and then superimpose my constant phi surface? Watch what happens as I move phi. Phi equals 0. Phi increases to pi over 2 and then keeps increasing to pi. So remember I said phi is connected with the word latitude? Well, if you think of your globe, then phi just gives us latitude on the globe. I love that. I think that's really cool. They did a nice job on this, didn't they? All right, well, okay, so that's what phi does. Phi tells you latitude. What does theta tell you? Theta tells you longitude. Look at that. So, just like you're used to on the globe, every point is represented by latitude and longitude, but now, well, if we don't want to stay on the surface of the earth, if we want to go below the surface of the earth or above the surface of the earth, we can. And that is really fun. All right, one last thing. The transformation between spherical and rectangular coordinates is a little more complicated because it's not like polar. And I've run out of time. I don't have time to show all of this to you. But I do recommend you're studying this.